Good morning, John Gilkison. It is Thursday, October 14th, 2021, and I wanted to shoot a video this morning on my PowerPoint presentation. I'm working on a new one, which is on aerodynamics, EVs, and towing with EVs. But I've only just started on that. And I had a PowerPoint presentation on electric vehicles, which I used at a city council meeting a few years back. And I was looking at it, and I still think it's pretty good. I had to update a few points in it, but other than that, now I've shot a video on this PowerPoint before. But what I was doing is I had the tripod set up in the camera, and it was off to one side. So the screen was at an angle, and it was just hard to see. And so I've set up today with the tripod and the camera right in front of the screen, square onto it. And I'm just going to be a disembodied voice behind the camera. So I wanted to prepare you for that, and I'm just going to go through the slides fairly quickly, and we'll see how it goes. So here we go. And we'll tilt it down a little bit. Now this is the one I'm talking about, aerodynamics and EVs, and I've got 17 slides so far. But I don't want to get into this today because it's not developed yet. I just wanted to give you a taste of it. We'll go back here to recent and the quiet revolution. How electric vehicles are poised to take over the marketplace. Why electric vehicles are our best choice for the future. And first we have a definition of terms here. And obviously BEV stands for battery electric vehicle, and ICE stands for internal combustion engine. PHEV is plug-in hybrid electric vehicle right here. BSFC is something I really don't want to get into the weeds on too much, but it stands for brake-specific fuel consumption in pounds of fuel per horsepower hour. And I think as we move to electric vehicle, that's just going to have to be amended to energy and just kilowatts. So and a horsepower hours, by definition, 746 watt hours. There are approximately 44 horsepower hours in a gallon of gasoline or the equivalent. British thermal unit, the amount of heat required to raise 1 pound of water 1 degree Fahrenheit. And miles per gallon and miles per gallon E or equivalent. There's 33.7 kilowatt hours in a gallon of gasoline, according to the EPA. So, Model 3, long-range battery specs, 75 kilowatt hour battery pack, 310 miles of range. I think it's higher now, 320 probably. 0 to 65.1 seconds. Top speed 140 miles per hour. Weighs 3,800 pounds. Has a coefficient of drag of 0.23. And down here says $40,000 Model 3 is due out in 2019. Originally I had that 35, but obviously that's needed to be amended. So here's a Model 3. I test drove this car. They're wonderful. a little too pricey for our family. We did finally get an electric vehicle after owning a plug-in hybrid electric for 4.5 years. We got a Chevrolet Bolt recently. I don't have a picture of it here. At least I don't have a picture of the car we own. So, these are definitions. If I was talking to a more technical audience, I think I'd probably want to get into these a little more, but we'll dwell on them here for a little bit. So if you want to freeze the frame or whatever, you could do that and read these. A lot of people don't know this, but Edison and Ford worked together on an electric Model T in 1916, and his aspirational goal was 55 pounds of battery per horsepower hour. He had over I kicked the tripod. He had over 400 pounds of battery in it. A Tesla Model 3 is at 9.8 pounds per horsepower hour. So it's obviously whatever 9 into 55 is, it's at least 5.5 times better as far as energy density goes, which is the reason it's for its performance. The physics of battery electric vehicles versus ICE. They're inherently more energy efficient, up to 4 times more energy efficient. That's what that brake-specific fuel consumption is all about. They have a brake-specific fuel consumption or energy consumption that's 3.5 times less. So most electric cars will get over 100 miles per gallon equivalent. So if you want to carry around 3 gallons of gas, you got to have at least 100 kilowatt hour battery pack. So it's amazing. I mean, a 75 kilowatt hour battery pack can get over 300 miles of range. So the physics of electric drive is just better than internal combustion engines. And there's several reasons for this. But basically heat engines are thermally inefficient. This is Chevy Volt. They're not really manufacturing and selling them anymore. There's still quite a few of them around. This is probably one of the best plug-in hybrid electric vehicles that's been made, in my opinion. It has 53 miles of range, and that's on electric only, and it's got 420 miles of range total with gas and electric. So you could drive one as a daily driver for local driving. You could drive one of these things for practically a whole year without ever using any gasoline whatsoever. So essentially they would be an electric car as far as you're concerned. And as a matter of fact, you would be forced to, by the computer, the onboard computer in the car would force you to run the engine for a while to use some of the gasoline, because the gasoline can go bad just sitting in the tank for a whole year. So here's the Chevrolet Bolt battery electric vehicle. We bought one in this May, and it's been a great car for us so far, even with the recall for the battery, which hasn't happened yet, but we're about to get upgraded to a 66 kilowatt hour battery. Ours is a 2019, which has a 60 kilowatt hour battery pack and 238 miles of range, not 258. But with this battery upgrade that we're going to get, we'll have a brand new Chevy Bolt, basically. And an 8-year, 100,000 mile warranty will start from whenever they put the battery in. So I think it's a win-win for us. Here's another option that's out there. This is a 2019 Kia Niro battery electric vehicle. I should upgrade this slide, given it's 2021. But the vehicle, even a 2021, is going to be virtually the same vehicle. This is a good option for people who want a small SUV or a crossover and still want to drive electric. Hyundai also makes the Kona, which I don't have here, which is a little less expensive and has even more range because it's slightly smaller. But it has the same battery pack and the same drivetrain. So this is kind of dated because the Biden administration has dropped this, lowering the CAFE standards. But anyway, the point I was trying to make here is it really doesn't matter what they do with the CAFE standards. Once you go to electric, you're automatically causing vehicles to get 3 to 4 times better miles per gallon. So a gasoline version of the Kia Niro would cost me $89 a month to run at current gas prices. Of course, I don't say what those are there. It'd probably be more now. But it would cost me $27 a month, or less than $30 a month to run it on solar grid type power. So I should redo this slide here too. This is your brake specific fuel consumption per horsepower hour. Basically, ICE cars run around 0.45 pounds of fuel per horsepower hour. They lose as much as 80% of their energy as heat. EVs are up to 90% efficient with brake-specific fuel consumptions of 0.15 and pounds of fuel per horsepower hour. And I should add the word right here, pounds of fuel. Well, I do, right there it is, -E, equivalent. I should spell that out though. This is why low energy density batteries compared to gasoline can still give EVs ranges of over 200 miles. And the cost per kilowatt hour, battery packs is dropping. It's below $150 now per kilowatt hour. And price parity is said to occur at around $100 per kilowatt hour. And this is going to happen in the next few years. And I believe it is happening with iron phosphate batteries, which are beginning to come out of China. Oh, I do have a picture of our Chevrolet Bolt. I misspoke, I just put it in. This is the 2019 Chevrolet Bolt that we bought with a 60 kilowatt hour battery pack and 238 miles of range. And if they upgrade the battery pack in the next few months, I'll have a 66 kilowatt hour battery pack and 258 miles of range. Well-to-wheel carbon emissions is something that's kind of hard to talk about. It's really hard to get good numbers on it, but a show called Fully Charged did some work on this several years ago. This is out of England. And so they were saying that even on coal-fired electricity, mind-to-wheel emissions for an electric vehicle is only 40 grams per kilometer. These emissions are CO2 is what we're talking about. Internal combustion engines are 120 grams per kilometer. But the ICE well-to-wheel, including everything from when you pump it out of the ground, is 450 grams per kilometer. And so an ICE mind-to-wheel is, an EV mind-to-wheel is 64 grams per mile. Now, all I've done is translate 40 grams into 64 grams by just, it's the difference between a kilometer and a mile. So, and your ICE, when you translate it to miles, your ICE well-to-wheel goes up to 720 grams per mile. You can see obviously it's about 3 times as bad. It's much worse when you go from well to wheel. This is a drawing a friend of mine did of a 0.13 drag coefficient vehicle. Aerodynamics is very important in electric vehicles because of the lower energy density of the battery packs as compared to gasoline. And right now, Tesla is a market leader with 0.23 drag coefficients, but the possibility is out there to do even 30% better. Now, there's 2 things you're going to notice about this, is that this whole frontal area here is, you don't need the hood for a big engine in front anymore. So you can take what was the hood sticking way out here, and you can use it for your aft body for the air to come back together. Now, you don't need this boat tail for city driving, but for highway driving, the speed's over 50 miles per hour, you do need it, and it could be deployable. So here I've just chopped off this is the way the vehicle could look without the boat tail. And it would be a lot more convenient for driving around the city if you had it set up with a deployable boat tail. So, I'm running over time, but so this is your aerodynamics not yet exploited. It's worth 30% improvement in highway range or MPG. For example, a Kona with 258 miles of range would have 335 miles of range if you lowered the drag coefficient down to 0.13. This graph's kind of hard to see, but it just shows the improvement in range with by lowering the drag coefficient. And again, you'd have to blow this up to really see it. This is my, hey, I'm going to Walmart, anybody need anything slide. This is a list of air pollutants coming out of gas and diesel powered cars and trucks, again by the EPA. And the joke that I always tell is that it's one of the advantages of or disadvantages, depending on your point of view, of an electric vehicle is you can't commit suicide in your garage. You can go sit in your electric vehicle in your garage with the garage all closed up and leave it running all day and night, and nothing will happen to you. So these are all bad things, and we all suffer from it. It's costing us tens of thousands of lives ended up early every year, and millions of dollars. Air pollution is damaging our health. This is global. EVs have far fewer moving parts, 200 versus 2,000 for a gas engine. They do not need oil changes. And this is kind of hilarious right here, because I got a piece of paper from Bravo Chevrolet that says I have free oil changes for the life of my vehicle. And it's an electric vehicle. I demanded they give me the paper so I could frame it. Using regen braking, brake wear is pretty much non-existent. So there's just a big reduction in servicing and the aftermarket industry for servicing with the adoption of electric vehicles. Here's an internal combustion engine with around 2,000 moving parts. I mean, this is an exploded diagram. You're seeing pistons, valve trains, springs, the whole 9 yards. And it's all these reciprocating parts. And the fact that it's a heat engine, which makes it so inefficient. Now that said, after 100 years of development, they've made it about as efficient as it's ever going to be. Same thing with an automatic transmission. Gasoline engines have a narrow torque band, so you have to have all this gearing in order to get the best efficiency out of the engine. And you can see there's just a lot of moving parts, and there's a lot to fail and rebuild, and they're very expensive to rebuild. Here's an exploded diagram of electric motor. There are no reciprocating parts. Everything's rotational here. There's not that many parts. And electric vehicles don't really have transmissions. You can retrofit an older vehicle with an electric motor and use the transmission in it if you like. And some people have done that. But the way electric vehicles work is the electric motor can spin up to 8,000 RPMs. And so you have to reduce that. If you to just drive the wheels, you just can't be spinning them around at 8,000 revolutions per minute. And the very act of reducing that really increases the torque. So a typical gear reduction is 8 to 9 to 1 or something like that, I believe. Don't quote me on that. But it's just a planetary gear set, and you can work reverse in by reversing the motor, I guess. I don't think they changed the into reverse in this gear reduction unit. This is an important graph, but essentially this is the electric power, the utilities, and they've gotten more green over time. As you can see, this is a trend. This is only up to 2017. So when you switch to electric vehicles, they really reduce the amount of carbon and input into the atmosphere, as well as other pollutants, even if you're running them off of grid power. So now right now you're not seeing transportation go down like that because electric vehicles haven't penetrated the market that much yet in the United States. Last year, in this year, I think we sold 1.8 million electric vehicles, which is double the amount the previous year. So it's going up pretty fast. But so transportation accounts for 27% of all carbon emissions. So emissions could be reduced to 9% or less with no other changes other than using EVs. But the cleaner the grid gets, the cleaner the transportation gets. So we obviously need to address heavy trucks, buses, trains, airplanes, and ships. So with solar power installed on your home, 240 volt charging, and battery storage at your house. This is what I call a home energy trifecta. We fill up at home. Charging at home will constitute the vast majority of your charging needs for electric car. This is one of the important point which I think a lot of people miss. You don't fill up your gas vehicle at home, so you have to go to gas stations every time you fill up. But with an electric car, 90% of your charging is going to be done at home. Depends on how much you travel, obviously, but I think we're pretty typical. We travel a couple times a year, and that's it. So we still need charging infrastructure, don't get me wrong, but we don't need as much as people might think. The whole point of this is we 80% charging is a loser. Um, you're just spending more for energy, and you really need to go to um, 240 volt charging, which is 90% efficient, and you'll have to buy less energy when you charge your car because you'll only lose 10% versus 20% of it trying to charge. Well, here's the point right here. 12 cents a kilowatt hour. It's equivalent to $4.49 a gallon. Now bear in mind you're going three and a half times further on that gallon of gas. So, but if you can get an off-peak rate for charging your electric vehicle from El Paso Electric, 5 cents a kilowatt hour, you'd be down to $1.87 for a gallon equivalent. I was talking about regen here. One of the tricks I use in Las Cruces is the east side of Las Cruces is at a higher elevation than the west side. So oftentimes we'll go to town on the interstate, do our shopping on the east side, and then go downhill to our shopping on the west side, and then take the old road home. And this is when you get below Unity. I've literally can start out on the east side of Las Cruces, let's say with let's say I got 40 kilowatt hours in my battery pack, and by the time I get to the west side of Las Cruces, I could have 41 or 42 kilowatt hours in my battery pack. And you can't do that with gasoline vehicles. Electric vehicles, motor doesn't run when the vehicle's stopped. They have very little latencies. It's the best stop in the world. And you're not wasting energy at a stop. And they have all their torque from 0 RPM. They don't need gears. Electricity is easier to deliver in the supply chain. It can be generated renewably. Drink electrons, not dinosaur juice. I figured out a gallon of gasoline equivalent in an electric vehicle weighs 1/75,000th of a gram if you're just converting energy into mass using Einstein's formula, E equals mc squared. So that's a little easier to transmit than 6.3 pounds. So over the next decade, they're going to get cheaper because battery prices are going to come down to parity. That'll probably happen in the next few years. And people are beginning to catch on. Anyone that drives an electric vehicle pretty much likes them and will want to buy one. So we're at the beginning of an S-curve. This is 3 years out of date. Now the thing you can imagine, if this is going this way, gas vehicles are going this way. So you've got an inverted S-curve for gas vehicles. So here's your S-curve. This is where we are now, right in this area right here, between the influentials and the early majority. And 10 years is all you need. There's a famous picture in New York City where they took a picture of a street. You could only find one gas vehicle in the street in 1901, and 10 years later they took the same picture from the same vantage point, and you could only find one horse-drawn carriage in the picture. And the reasons people switched were cars cost half as much to operate as horses did. EVs cost half as much as fossil fuels to operate and could reach cost to buy parity and within 5 years. They're clearly superior, and you really need to go for a test ride or a test drive of an electric vehicle. If you've never done it, you need to do it. So that's all I have for you here. I ran twice as long as I need. or should run on my videos, but we'll see how this goes trying to upload this monster. Take care, everybody. We'll see you on down the road. Bye-bye.